Welcome to Advanced Quantum Chemistry and the second lecture on density functional theory. Density functional theory is actually a very old method, although it might not have been called density functional theory right from the beginning. But the Thomas-Fermi model for atoms, which was published in 1927, is actually density functional theory. They had an expression for the energy of an atom, which had three contributions. It had a contribution, a kinetic energy contribution, electron-nuclear attraction contribution, and the electron-electron repulsion contribution. And whereas the electron-nuclear contribution and the electron-electron repulsion contribution are precisely the same contributions as we would have them in the Hartree-Fock theory, just written now here with densities instead of with just orbitals, but with the expression for the density of one electron, which we had in the last lecture, you can rewrite that in precisely the form we had in Hartree-Fock theory. But what is new and different is that kinetic energy contribution. And here they described the electrons in an atom with an uniform electron gas model. And from this they could derive this expression, this functional form for the kinetic energy, where we have an integral over the density or the density to the third power, and then multiplied with some constant. Now a few years later, this Thomas-Fermi model was extended, probably by Dirac, and is therefore called the Thomas-Fermi-Dirac model, with an exchange contribution. Because one knew from Hartree-Fock theory that if you have an antisymmetrized wave function, which the wave function for electrons should be, there should be an exchange contribution. So they derived a functional form again for this exchange contribution again, and it is very similar to the kinetic energy term, but now it's density to the 4/3 power with some constant. And you can see this exchange contribution depends only on the local value of the density. It's an integral over the densities, but it's you have, as the integrand under this integral, you only have the density to a certain power. And that is different to the exchange contribution in Hartree-Fock theory. Actually, one can write the exchange contribution in Hartree-Fock theory also in form of an integral over some kind of a density, as is done here, but it's a different density than this one, because this density has two variables, 1 or 2, so it depends on 2 points in space, and it's written like this, so it's a sum over all occupied orbitals, and then the first orbital complex conjugate at point 1, and the second then at point 2. If we insert this 2-point density here, remember this is norm squared. So if we insert that in that integral, have a double sum, and of course means that in the first part, in the first integrand, we have then I, and for the second one we have to choose a different summation index, so let's choose J. Then we get the complex conjugate from R1, and in the second one, J, because the second one is then also complex conjugate, the one for R2 becomes J. So inserting this one in here and keeping track of the complex conjugations, we can write it up like this, and then you hopefully can recognize this just as a normal exchange integral as we had defined it in Hartree-Fock theory, showing that this is actually just another way to write the exchange contribution to the Hartree-Fock energy. The next important contribution in the history of density functional theory are the Hohenberg and Kohn theorems from 1964. Walter Kohn, by the way, got the Nobel Prize together with John Popel precisely for his contributions to density functional theory. Now the first theorem is the proof that the assumption that the energy can be expressed as a function of the density is actually correct. The second one is that there also exists a variational theorem, as for wave function based quantum chemistry or quantum mechanics, which says that if one calculates the energy with a trial density, then the energy one obtains will always be larger or, in the best case, equal to the exact energy. And it will only be equal to the exact energy if one, by any chance, used the correct density. The trial density, however, has to fulfill the condition that integrated over the whole space, it sums up to the number of electrons. But for using this variation theorem, of course, one needs to know what the exact functional is, what the exact expression for the functional is. And that is so far unknown. So the question is how much one can use that. Now, the Thomas-Fermi model and the Thomas-Fermi-Dirac model described in the previous slides are first examples of what is called orbital free density functional theory. The only thing one really needs in order to calculate the energy are the density. The reason why you probably haven't heard about those in chemistry is that the accuracy of these orbital free density functional theories are too low. And the reason for that is that the expression for the kinetic energy functionals is not good enough. So the results one obtains are simply not good enough to be useful for quantum chemical calculations. In the next lecture I will talk about another form of density functional theory where this is no longer the case.